Today I'm going to attempt to give you an overview of a massive part of dark matter parameter space, dark compact objects. I'm taking a lot of the stuff that we had thought about this morning and moving it into the dark sector. This is the dark versions of the things we've been thinking about so far. And my hope in talking about this is that I can inspire opportunity to collaborate. I see a lot of opportunity to do so, both with people who think about star and galaxy formation, as well as people who are working on gravitational waves and gravitational lensing. So, to get into this, the way I'm going to go through this talk is we're going to ask, what are dark compact objects? Why are they worth thinking about? How do they form? How can we observe them? And then finally, what can we do going forward with what we've come to understand about them? So starting with the most obvious question, what am I talking about? And this actually proved to be quite tricky. There's an enormous taxonomy of things that could fall under the umbrella of dark compact objects. The definition that I'm choosing for myself is an overdense, and I mean compared to a dark matter halo, bound collection of dark particles or exotic states of matter that are too heavy to be composed of a single particle, even if you allow that particle to be quite heavy. And there is a massive variety of things that fall into this category, great variation in both mass and density. And if you're looking in the literature, you may see these objects listed under many names. I've tried to list a few things like blobs, clumps, composites, darkos, dark stars. I actually ran out of space once I started including things. There are so many names these things fall under. So if you happen to see a collection of particles bound together, what I'm describing today probably applies to those. But some examples of dark compact objects that you might see in nature: primordial black holes. Yes, I'm including them in this category. They behave quite similarly. Axion stars and boson stars. Things like quark nuggets and asymmetric dark stars. So there's quite a range, again, of mass and densities in the sorts of objects that fall in here. And the question would be, why are these objects worth thinking about? Well, I will remind the audience, we have not yet figured out what dark matter is. And in the search to try to understand what dark matter is, we've got this enormous range of masses about what dark matter could be, and dark compact objects fall here right up at the highest end of masses. Now, we've all seen this plot in multiple talks. In reality, the amount of parameter space taken up by dark compact objects is a lot bigger than usually depicted. Almost more than half, depending on where you put the cutoff, of dark matter parameter space would have to be occupied by things that are quite heavy and probably made of many particles coming together in some way. So this is one reason that these might be worth our attention. In addition, I will remind our audience again, we have not yet found dark matter, and it's worth asking why that is the case. So to illustrate this point, I have a plot here showing direct detection constraints and reach for various different experiments. And what you'll see is there's a common shape. At the low end, we lose sensitivity because effectively as masses get low, the interactions become too weak for detection. But at the high mass end, the problem that we run into is that the dark matter particles become too scarce. As they get heavier, they become less abundant, and it becomes less likely that we're going to see them in one of our detectors. To put this into perspective, we get about a Planck mass worth of material per meter squared per year on the Earth. For our best dark matter detection detectors, that's about 1/10 of a milligram over 10 years that pass through that detector. If we were to employ our best neutrino or largest neutrino detectors, it's about 50 grams over 10 years of observation. And using the entire Earth, it's about 10 to the 17 grams, about the mass of an asteroid over 1 billion years. And so the point is that if dark matter were to cluster or clump into structures that are above these different mass thresholds, it becomes increasingly difficult for us to detect them by traditional means. And that may be one way it's been avoiding us. And then the final point I'd like to make is that dark compact objects don't need to be all of the dark matter. They could be a component of a more rich and complex dark sector. These could be parts of an exotic cosmology, and oftentimes they emerge as a result of these, either through phase transitions in the early universe, enhanced perturbations at small scales, and We can argue about how exactly or when exactly this happens, but also as a part of many scalar dark matter theories. So this is why I think dark compact objects are worth thinking about. So let's talk about the different ways that we can make these objects. Now, again, there are a lot of different ways we've thought about how to do this, thanks to the boundless creativity of theoretical physicists. I'm not going to talk about all of these. I'm going to focus on the ones that I've done the most work on. But we have many options, such as collapse of enhanced overdensities, often used to make primordial black holes. We have strong self-interactions that allow structures to build up. You could think of a quirky dark matter as an example. We've got phase transitions, also a way to make black holes, potentially a way to make quark nuggets, Bose-Einstein relaxation to get axion stars. And then finally, the one that I've done the most work on. Ooh. All right, never mind. We're thinking about dark dissipative interactions. So what I mean by this is when dark matter particles can scatter off of each other and lose energy in the process. And this is a way to let a dark matter halo cool. To illustrate how we get dark compact objects from this, I'm going to start by showing you the way we get dark matter halos from dark matter that doesn't have any self-interactions. So how this happens, we're in a matter-dominated era. The universe is seeded with various density perturbations, and these perturbations are going to grow, assuming that they are both small compared to the Hubble radius and large compared to a gene's length, which is the scale at which a ball of this material can support itself against collapse. Assuming those conditions are met, these perturbations are going to grow linearly as the universe expands, and then when the density is about twice that of the background, these overdense patches will decouple from the expanding background of the universe, begin collapsing on themselves under their own gravity, and virialize. This is sort of a cartoon story of how we get the dark matter halos that we know and love. Once we introduce interactions, there are extra layers and extra flavors to this. So first off, self-interactions are going to change sort of the preferred scale that these things are happening at because they can change pressures in the gas, and so they can change the gene's length. But beyond that, this process should kind of progress as it had before, up until we've got the halos. Now that we have these strong self-interactions, they can release energy from the halo, allowing it to collapse either collectively into one ball, potentially making a black hole, if these objects are, if cooling is inefficient, and if cooling is very fast, it can cause the halo to break up and fragment into many smaller compact objects. And your choice of cooling mechanism is going to have a really strong influence on the sorts of objects that you make. So as an example to illustrate this, this is a sort of specific dark sector that we considered, where we have two different dark fermions and one dark photon. The effect is that it gives you two different ways to cool one of these halos, which I realize is much simpler than what we're dealing with in the standard model, but it's a bit for the dark sector. So we've got bremsstrahlung, where particles scatter off of each other and emit a dark photon, losing energy that way, or collisional excitation and decay, where particles can scatter off of each other, excite to a higher energy or higher mass state, and then lose energy as they come back down to the lower energy state, emitting a dark photon. These processes, this is temperature and number density for our dark halo. These processes are going to dominate in different parts of parameter space for our halos, and they're going to very much dictate the way that these dark matter halos evolve and break up into smaller objects. So the way that you should sort of understand this plot is that in this region, along this black line, our halos are virializing, and when they cross over to this blue line right here, that's where the halos are virialized. They're going to cool following these blue lines, and they're going to cool as one single object until cooling becomes very fast and efficient, at which point they would begin breaking up and fragmenting. How they fragment is really dictated by the shape of this cooling region here. And to just show you sort of how that really shapes the objects we get, we can look at the mass contours of the typical fragments we expect to get from this process. As I've highlighted here, the shape of these contours is pretty much exactly following the shape of that cooling efficiency region that we saw previously. So again, the specific processes available to your dark matter are going to very strongly dictate what sorts of things it becomes as it cools and evolves. Now, at this point, you might be wondering, wait. Aren't we not supposed to be allowed to have these strong self-interactions? The bullet cluster. Oh. I'm just not having good luck with this. Okay, well, the bullet cluster should limit these interactions to be, for dark matter self-interaction cross-sections, to be about less than 1 centimeter per squared per gram. But again, thanks to the boundless creativity of theorists, there are many ways to avoid these and still get interesting dark matter compact object formation and self-interaction. And so a couple of ways that one can deal with this is, put simply, you work with particles that are very heavy with interactions that are very short range, and ones that may only be relevant very early in the universe at very high densities, so that the evolution might start at early times, or perhaps in exotic cosmologies. And I'm going to get into that in a little more detail in the next slide. You can have interactions that are quite strong and only relevant, again, sort of at early times and early conditions, and then neutralized because the structures they've formed no longer interacting. Think like a quirky dark matter sort of situation. And then the last option that we see this a lot in atomic dark matter scenarios is that the dark matter that self-interacts might just be a small fraction, say less than 10% of all of the dark matter. But focusing sort of on this early universe scenario, one way that we've thought about how to get interesting structure formation without having to worry about some of the limits on dark matter self-interactions comes from thinking about an early matter-dominated era. So this is allowing matter domination to happen prior to BBN. In this case, interestingly, structure formation progresses pretty much exactly the same way as it would in a late matter-dominated era, with the exception that the typical scales, length scales and time scales are a bit different, decidedly smaller. We get out of the matter-dominated era in a variety of ways. The one that we looked into was a phase transition or period of thermal inflation that would return the universe to radiation domination, as long as some of the dark matter halos had had time to virialize. They shouldn't be ripped apart in a thermal inflationary scenario, just sort of pushed apart and diluted overall. And then we're in standard cosmology, and our halos, which are now incredibly overdense compared to the universe, have lots of time to self-interact, radiate, cool, and evolve into even more compact objects. Okay, so given the vast diversity of objects that we can make, it's worth asking how we can look for them. And thankfully, we can rely on a lot of the work that's already been done by people who search for primordial black holes. Dark compact objects are going to share a lot of features with them, with the exception that as they get more puffy, properties of primordial black holes, that analogy starts to break down. But we can rely on things such as gravitational lensing and the formation of binaries of these dark compact objects. We can look for gravitational wave signals from those in-spirals, contributions to the gravitational wave background, both from the in-spirals and from some of the exotic cosmological scenarios that allow us to create these dark compact objects. And one that I'm particularly interested in is dark radiation. Most of these dark compact objects are forming because they are a lower energy bound state than the free-floating dark matter in one way or another. For them to get into this lower energy state, they need to release energy in some way. If this is happening quickly or at specific times in the history of the universe, they can emit a significant amount of energy, significant compared to their mass, into the universe as dark radiation. And this is an avenue that, while I have not looked into yet, I think is very worth exploring more carefully. And then finally, we have stellar dimming, an option for dark matter dark compact objects that have some interactions with light. But of course, as we get into specific dark sector models, there's a lot more you can do. But going to touch briefly on gravitational lensing, there are many different ways to take advantage of this. I've been having some really interesting conversations about astrometric observations through Gaia and using that as a way to look for heavy objects. I think those would be very, very relevant here. But at present, microlensing surveys such as Macho, Subaru, Ogle place some of the strongest constraints on black holes and dark compact object populations, where the basic idea is that one of these heavy objects should pass between us and a distant star, brightening the light from that star. So these observations work really well for objects that are heavier than 10 to the 21 grams. However, there are ideas out there if you want to go to lower masses, including femto and pico lensing, though those are still very much being sorted out. And the other sort of limiting feature with these sorts of surveys is that you need your object to be quite compact. It has to be smaller than an Einstein radius, which for the Eros or Ogle type surveys is about 10 to the 3 solar radii for a 1 solar mass object. As these objects get as these objects get larger and puffier, lensing starts to break down. However, we could instead rely on this stellar dimming effect, where if any of these objects have interactions with ordinary light, they can scatter light from stars they pass in front of, and that actually we don't have to do much new work to look for this. Existing exoplanet surveys and even existing microlensing surveys are sensitive to this sort of stellar dimming. And fortunately, as Yang Bai figured out quite recently, dimming from these light curves of a semi-transparent thing passing in front of a star should look different than dimming from a fully opaque baryonic object passing in front of a star. And so it's pretty exciting because we do get access, we get to use these existing surveys to get access to new sorts of objects that they themselves wouldn't otherwise be able to look for. So another way that we can approach looking for these objects is through gravitational wave signals, specifically from inspirals and mergers. Now, we've been talking about looking for astrophysical objects in spiraling and merging, but dark compact objects will also often form binary systems in the early universe, and some small fraction of these are going to be spinning down and merging even in the present. An approximate rate for this is about 10,000 events for a 10 to the 15 gram mass object in the Milky Way. So that's per second. This ends up being much smaller as you go to higher masses, so it doesn't look quite as crazy. But what's also interesting, other than just seeing mergers where you may have violent events when a collision happens, or where we can look for in-spiral gravitational waves, is that as these objects get puffier, their waveforms start to look different from that of ordinary primordial black holes, and this is actually something that has been calculated for a couple of different objects. So just to give you a sense of scale, like what sort of things are we looking for, what are the targets, based off of the rates I just showed you on the previous slide, this is a contour plot showing the peak strain in pink and the peak frequency, the gray dotted lines, of in-spiraling dark compact objects. This is sort of the brightest thing we would see in 1 year of observation, given this rate, and assuming that they only make up about 1% of all the dark matter. The green band here, the purple band here is the LIGO frequency range, and the turquoise band is the LISA frequency range, just to give you a point of reference. But we don't need to just rely on these. We can also look to the stochastic gravitational wave background. There are multiple ways of doing this, not just the sort of generic formation of binaries that want to spin down and merge, though this is happening over the history of the universe, but also the exotic processes that helped get us these dark compact objects in the first place will often leave gravitational traces in the gravitational wave background. So looking at the first, the collective effect of many different dark compact objects in spiraling over the history of the universe, For dark compact objects with these highlighted in red properties, this is the mass down here, this is its radius in terms of the Schwarzschild radius. These should have contributions, which would be observable to LISA, if the dark compact objects are making up about 1% of the dark matter. Then over here, this is work by Josh Foster, Nico Fernandez, Ben Lillard, and Jesse Shelton, where they looked at early matter domination scenarios where dark structure was allowed to form at least a bit during the early matter domination. And what they found is that depending on your sort of choice of scenario, you can get gravitational wave signals that should be observable in the present. So that's a lot of ideas about what these things could be, how we could look for them, and the question is, what's next? How can we work together to better understand these? Well, I'm interested in improving the predictions on dark compact object populations. We've been using fairly rough approaches, so working with more stellar-style simulations, understanding how these objects might merge and grow over time. In addition, if we have models that are particularly exciting, it could be worthwhile to try to predict and search for waveforms from in-spirals of these things, or search for possible contributions to the compact object, the gravitational wave background. And then finally, I think what I'm most excited about is understanding the way that dark radiation from these objects will impact cosmology. But of course, I'm talking to all of you about this today in hopes of inspiring conversation and more ideas, so I'm always interested in hearing what your thoughts are on this. So what I hope you'll take away from this talk is that it is a worthwhile endeavor to try to understand the dark compact universe, both as dark matter models in their own right, and as a way to better understand broader cosmologies and broader sort of complex dark sectors. There's a lot of opportunity to collaborate in thinking about this, and there is sort of a rich and diverse parameter space, both from a model building and a phenomenology perspective to explore. Thank you.
Okay, thanks for the great talk. We have some time for questions. Shabik? Oh, sorry.
Thanks for the nice talk. So could you comment a bit on, for the gravitational wave signatures, comment a bit how well do you understand, for example, the distribution of these compact objects, the mercury, things like that, like do you simulate these, or is it mostly on the
Yeah, so the estimations of the simulation rate come from analytical estimates of assuming, the objects have all have the same mass, basically, and they have sort of a random distribution. This just comes from thinking about what fraction of them sort of have the right initial conditions to form binaries. I do think there's a lot of interesting work one could do thinking about with simulation, spontaneous formation of binaries through sort of like multi-body dynamics. And I do think there are arguments that that might even be a dominant effect.
That's precisely the slide I was going to ask you about.
Yeah.
So when you say that these compact objects form naturally, can you say how they do that? Because as we heard in the first talk, it's quite difficult to do in a standard model to take two objects and get them to merge within a Hubble time.
Mm-hmm. Yeah. So the idea behind this is sort of stolen from primordial black hole work, where the assumption is that these primordial black holes are present at sort of extremely early times, and at that point you can actually rely on the expansion rate of the universe to be sort of removing energy from the system. And so they get caught into these sort of gravitationally bound binary systems at these early times because of that. And you're sort of looking at a statistical distribution of them, and then most of them are not spinning down today. This is really just a tiny fraction of them. But because at these lowish masses, there are many, many of these objects, if they were to be all the dark matter, so you can still be somewhat successful with only a tiny fraction of them merging today.
And I had the same question, actually. So when, slightly earlier, you were talking about how you have this early phase of matter domination. And extra inflation to get rid of that and then to radiation. Did I understand that correctly?
Yes.
What's the physics driving the second phase of inflation?
So the period of thermal inflation is an unstable scalar field. And so once the energy density of the universe falls sort of below that of the scalar field becomes the dominant thing. And so then it's driving inflation. And when it decays and implodes, that's what gets you back into matter domination.
So this sounds more similar to dark energy than inflation in the sense that it sounds like you've got a very light scalar with mass that's tuned to give inflation around that time. Are there any fine-tuning issues associated with that?
It depends how much of your dark compact objects you want to be the dark matter. So to some degree, potentially, because you want the inflation to happen after you've allowed some of the dark matter halos to form. And so if it happens too early, you're not going to have any halos that survive, and it's more a matter of like what fraction of the population you would like to be dark halos. So as you wait longer and longer, more and more halos can form. Yeah, actually, I'd say no, it's not, now that I'm thinking through it, I would say it's not too fine-tuned in terms of when it starts. You just have to make sure it ends fast enough that you haven't completely blown all these objects away. And so there might be a bit of fine-tuning in there, in ending it so that you haven't over-diluted the universe.
Okay, maybe we have time for a quick question. Marius?
Is very constrained, so presumably you need something extremely dense to get that to be an effect you could only possibly see from the compact dark object. But of course, if it's too dense and too big, then you also get gravitational lensing and things. I'm just curious, like, what is the density? What's the mass of this object that you'd get the dimming from, and like, what's a good model that would give you that?
Okay, so can I show you a plot after? It would be easier for me to point it out on a plot since I don't actually have this in my slides. But so, you know, an asymmetric ball where the particles are carrying sort of a dark Miller charge can potentially do the trick.